Okay, so welcome to Math 150. This is lecture 8. And so what we're going to do today is we're going to continue with applications of Taylor series. We're going to use this to finish reviewing chapter 10. So you should have already started working on some of the homework problems. You should have already started reading the stuff from chapter 12. Build up as much of a strategic reserve as you can. We'll see some applications of what we're doing today in terms of how to reduce, I think most, if not all, of the trigonometry you've done to 5 minutes. So if you ever need any trig identities, calculus is a great way to derive them. And we'll use this as a motivation to some of the big concepts we're going to have in multivariable calculus. And so, right now we have, oops, clicked the wrong thing. Right now we have not, seen too much of multivariable calculus. Right now we've been learning more the language we need, the tools we need to be able to do it properly. That's going to continue in the next chapter when we start talking about vectors. So it's going to be a while before we have the language we need. I have been able to move up my appointment with the dentist to reinsert my tooth. I cannot get too excited today or I will be in a great pain. So if you see me start getting too engaged in this lecture, just please do something to stop. All right, this was the homework problem you're supposed to do. You're supposed to think about the Taylor series of f of x equals cosine x sine of x. And I give you, the standard questions to ask. Just like when you meet someone on campus, what's your name, where you're from, what are you interested in studying? First thing you ask when you see a series like this is, can you calculate the Taylor series? Does the Taylor series converge? If it converges, does it converge to the original function? So can anyone tell me a way that we could calculate the Taylor series? So again, depending on how extensive you want your notation to be, the Taylor series of f of x is, t, and I'll put a subscript f to remind myself that it depends on the function f, is the sum, n goes from 0 to infinity, of the nth derivative at 0 over n factorial x to the n. And note that if we take the nth derivative at 0, that's just equal to the nth derivative of f at 0. And that's why we have the n factorial, because when we take n derivatives, n, then n minus 1, then n minus 2, all the way down to 3 times 2 times 1 is going to come down, and that will cancel. So can someone tell me, how would we find the Taylor series of cosine x sine x? What would we do? So you should have been thinking about this. How would you calculate the Taylor series? Yes.
For the first one, you don't need that.
Good. So f of 0 is pretty easy. It's cosine 0 times sine 0. One of them is 0. That's 0. It's sine that's 0, but for this one, I don't really care. I just need to know that one of them is 0. All right, what would I do for the next? What goes next? Oh, and what rule do we use? Product rule. So the derivative of cosine is minus sine. So you get minus sine x plus derivative of sine is cosine. So it's going to be cosine x. So if you want, this is cosine squared of x minus sine squared of x. So what's f prime of 0 going to be? I'm sorry, no, f prime of 0. When we take x equals 0, what do we get? We just get 1. All right, now we need the second derivative. How do we calculate the second derivative? So either the chain rule or the power rule. Either one is an acceptable answer. When you have cosine to the second power, you might think power rule, but it's also the chain rule. Either one works. So we would get 2 cosine of x, and then derivative of cosine of x is minus sine of x, right? And then we have minus 2 sine of x, and the derivative of sine of x is cosine of x. So what does this equal? Minus 4 sine of x cosine of x. I'm sorry, I'll do cosine of x sine of x. Yes? And what is f double prime of 0 equal to? Just going to be 0. Now, It's a little bit early in the semester for you to understand just my warped sense of humor and whatnot. Initially, does this look like a fun problem to do, calculating derivatives, high derivatives of cosine x, sine x? It turns out, however, it's not that bad. If we take two derivatives, we almost get back to where we started. We just have an extra factor 4. So this is just going to be -4 f of x. So every time I take two derivatives, I return to where I start with an extra factor of -4. So if I actually wanted to calculate the next derivative, it won't be that bad. So f triple prime of 0 would just be, I would now have an extra factor of -4, so it would just be -4. Right? Oh, I'm sorry, wait a minute. Right, it would be -4. And then the fourth derivative at 0 would be 16. ... So that's not so bad. Okay. There are two other ways to do this problem. The more ways you have to do a problem, the better. So let's look at the function again. So we have f of x is cosine x sine of x. Mathematicians are lazy. So reduce to something known. We know the Taylor series for cosine of x. This is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus ... This is the sum. N goes from 0 to infinity, -1 to the n, x to the 2n over 2n factorial. And this is one of the famous Taylor series I included at the end of the slides. This is one of the ones you just should know. Okay, you can rederive it. And what you notice is when you take derivatives of cosine goes cosine, negative sine, negative cosine, and then sine, and the derivative of sine is back to cosine. So it's cyclic with period 4. And this is why you have these things basically, 1, 0, -1, 0, 1, 0, -1, 0. Notice that all the odd powers have a 0 in front of them. I know what sine of x is. Sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus ... And that's the sum, and goes from 0 to infinity, -1. And it just takes me a second to just remember how I want to write this. So when when the power of x is 1, I want a positive sign. So I want -1 to the n plus 1. And now note when n equals 0, I'm going to get my power of x will be x to the 1st, good. I'll have a 1 factorial down below, and I want the sign to be a +1. So -1 to the n plus 1 works. Could I have done -1 to the n minus 1? Yeah, that would have been fine. So here's my expansion for sine of x. Okay? Yes.
When n equals 0, you want a positive, right?
Yeah. Oh, did I slip up?
X is n equals 0.
Oh, okay. Oh, good. Thank you. So when n equals 0, then I don't want the 1 at all. Thank you. So I want to do it like this. Thank you. So I did the check, but I did not do the check correctly. All right. So I know cosine of x, and I know sine of x. So cosine x times sine of x should be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus ... times x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus ... And now all I have to do is multiply things out and group things that have the same power of x. So is there any way I'm going to get a constant term when I multiply these two things out? No. All of these have even terms, all of these have odd. So the smallest I could have is x to the first, which is 1 times x. Okay. Is there any way to get an x squared term? No. How about an x cubed term? Yeah, there are two ways to get an x cubed term. I could have 1 times negative x cubed over 3, and I can have negative x squared over 2 factorial times x. So to get the x cubed, I could have 1 coming here, and I could have x squared coming here. So for the x cubed term, I'm going to have negative 1 over 2 factorial from the x squared hitting 1. And then I'm also going to have the 1 from the constant term hitting the negative 1 over 3 factorial. And then you just keep going like that. And so I have negative 1/2 minus 1/6. So that should be minus 4/6 or minus 2/3. Or x minus 4 over 3 factorial x cubed plus dot, 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 dot. There's a lot of great things about this problem. Which would you rather write, 2/3 or 4 over 3 factorial? Two-thirds. You know, I understand the number 2/3 a lot better. Why is 2/3 a nice number? What's the property it has? It is. So 2/3 is the same as 4 over 3 factorial. What word do we use to describe something like simplified, reduced, lowest? You know, I've removed all the common factors. But for this problem, it's actually better to write it as negative 4 over 3 factorial. Why is that better? Well, because if you look at how we write the Taylor series, we write it as the nth derivative at 0 over n factorial times x to the n. So if I leave an n factorial down below, I can identify the top as the value of the nth derivative at 0. So if I look at what I had over here, the 0th term is 0, the first derivative is 1, the second derivative is negative 4. And so what we get is, whoops. One of those days. I'm trying to write on the bottom of the screen, which is not a good idea. So we get the Taylor series is going to start off with no constant term, 1 over 1 factorial, so it'll just be x. Then we have negative 4 over 3 factorial, x cubed plus dot, dot, dot. That's exactly what we're getting the other way. And it just makes it a little bit easier to recognize this if I keep the n factorial on the next slide. So this is another way to calculate Taylor series. If I know two functions Taylor series and I multiply them, I just multiply the Taylor series. The proof of this is to just use properties of the derivative. You know, we have the product rule, we can go through, we can roll up our sleeves. So if you know derivatives of, and if you know Taylor series of simple functions, you can get more complicated functions very easily. This is a huge theme in the class. Reduce to something you already know. Yes?
Why do you, like, how are you allowed to say that to them for like x to the 2 and the next one is x, or sine x is x to the 2 and plus 1?
Well, this is just actually calculating the Taylor series of each. So, was it here? Right. So this is just the Taylor series of sine, cosine, and e to the x. These are just three very famous ones. And the way you do this is you just find the derivatives. So what's nice is they repeat with order 4, because we just saw cosine goes to minus sine, goes to minus cosine, goes to sine, goes back to cosine.
So that will only work for like these 3.
Well, these are just 3 very important ones. The natural log of 1 plus x and the natural log of 1 minus x, eventually we might need to learn those as well. It's sort of like your multiplication tables. You can always rederive these from scratch, but they're so important that it's just useful to remember these. And so they all come from e to the x. And what's the nice property about e to the x and its derivative? It's just e to the x. Oh, I'm sorry, I didn't mean its derivative, I meant its integral. It's just e to the x. It's really nice. It doesn't matter, am I integrating, am I differentiating? You just get back where you started. Sine and cosine are somewhat similar. It takes a little bit longer, it takes 4 times rather than once, but you get back to where you started. And we have all these angle addition formulas from sines and cosines. They're all inherited from e. And it's because e to the ix is cosine x plus I sine x. And the way we see this is actually what we mean by sine and cosine. How did you initially define sine and cosine back in high school? SineCosine. So I always have to get the mnemonic by remembering what the definitions is. So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So they're defined in terms of a triangle where the hypotenuse has length 1 and you have a right angle. It turns out that those formulas are only good for getting a few very special angles here, the 30, 60, 90 triangle, the 45, 45, 90 triangle, and some things we can do from that. We can have angles and get things nice, but for arbitrary angles, we can either do some kind of infinite limiting process with your lines going all over the place, or we can use these formulas here. And this is really how sine and cosine are defined. And so what we're doing here now is we're using our knowledge of the formulas for sine and cosine. And by just using the summation notation, it's a little bit more compact. So when you're trying to write things down, I can write down all of these terms, or I can write it more concisely like this. As you go further and further in mathematics, you use less and less notation. One of my favorites at the side is due to Feynman. He reduced all of physics to one equation, u equals 0. Now, what is u? U is the unworldliness. It's, f minus ma squared plus e minus mc squared plus. You basically just take every physical law in the universe, subtract the left-hand side from the right-hand side, and square it. So the only way that this can be satisfied is if each individual component is 0. So his point of doing this is just, look, I can reduce all of physics to one equation. That doesn't mean I've made progress. That doesn't mean it's something that I can see and understand. You have to decide what notation is going to help you understand what's going on. This is far more concise to write. I like to do at least both, at least early in the semester, so that I can just look at it and see what's going on. When I'm multiplying things out right now, I find it much easier to write it like this with the dots than to write it with the sums, so I can just see what's going on. All right, so we've already solved the problem 2 different ways, right? We should do it at least 3 different ways. So let's do one more solution. So we have f of x equals cosine x sine of x. There is another way to solve this. Does anybody know another way of writing cosine x times sine of x? So much of life is about, can you recognize things? What if instead I gave you f of x is sine x cosine x? Does that remind you of anything? So sine x cosine x, does that remind you of anything? Sine 2x, what's the sine of 2x? So what if I write it as 1/2 2 sine x cosine x? Then it's just 1/2 the sine of 2x. And so to me, I think it's easier to see sine x cosine of x and think of the trig identity because we're just used to seeing it in that way. It's the same function. And so this is the third method. It's almost like a u substitution. So I know the sine of u is u minus u cubed over 3 factorial plus u to the 5th over 5 factorial minus u to the 7th over 7 factorial plus dot, dot, dot. Let u equal what? What would I want to take for u here? 2x. Thus, 1/2 sine of 2x would be 1/2. And then I just take the expansion for sine of u, and I just replace every u with a 2x. So I would then get 2x minus 2x cubed over 3 factorial plus dot, 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 which is 1/2 2x minus 8x cubed over 3 factorial plus dot, dot, dot. And this is just going to be x minus 4x cubed over 3 factorial plus dot, dot, dot. And there we go, the same answer as before. And now you can really see why you're increasing by a factor of -4 every time you go 2 more. So we've reduced this. It's really just, what is the Taylor series of the sine of 2x? Okay, so these are 3 very powerful ways to calculate Taylor series. Let's just talk about some applications. I'm not going to do this, but how many of you would be comfortable taking a test on trig identities right now, where you have to prove them? So you would have to prove the angle addition formulas. I mean, if my hand doesn't go up, you should be, concerned, right? I'm not going to bother drawing the circle really well. I'm going to try to remind you of things you might have seen before. So let's say that this is a unit circle. And then let's say this is my angle x. This is my angle y. If you remember your trig, the goal in trig is to draw auxiliary lines, to draw extra lines and get as many right angles as possible. Why do we like right angles? Well, right angles give us right triangles. We know Pythagoras, we can do things. So I'm going to drop, and I'm just going to keep dropping lines. So I'll drop a line coming down here, and that will give me a right angle. I'll make that red, actually. So I'll drop a line down here, and that gives me a right angle. I'll drop a line down here, and that gives me a right angle. So I know this whole distance here is cosine x, and I know this whole distance here is cosine y, and I have similar stuff going up and down. Well, there's other right angles I can draw. I can draw a right angle. I can draw a right angle to this triangle here, and then I can draw a right angle coming down like this. Okay. And so now, if I look at this dotted line over here, what's the length of this green line? Well, that's a hypotenuse, so that's 1. This over here, that's got to be the sine of y. And so I'll put some points over here. We'll call this O, and I'll call this point A. So OA would be the cosine of y. Does everyone agree with that? It's from the triangle OAB. It has hypotenuse 1. OA is the side that's adjacent to the angle y. Now, let's call this point C over here. Look at triangle OAC. We know the length of OA is cosine y, so the length of OC is going to be cosine of y I'm sorry, it's going to be What's the length of OC? That's the hypotenuse times, yeah, it's the hypotenuse times the cosine angle. So I was right. So it's going to be cosine of y times the cosine of x. Okay. Oops, I have one typo here. Sorry, this is not cosine of y. What is this the cosine of? This is the cosine of x plus y. This distance over here, I'll call this point D. That's the cosine of x plus y. It's OA, that's the cosine of y. So do we know enough to calculate the cosine of x plus y? So let's look at all the different stuff we know. We know OC, right? OC is cosine x, cosine y, but we've overshot OD by DC. Right? So we have to figure out what is the length of DC. Well, fortunately, do we agree that DC is the same as that length over there? And is that the same as this length over here? Well, now if we do that, we don't have nearly enough letters. Let's let this be the letter E. We now have a right triangle over here. And so we know that DC is the same as EA, right? And so now we have to match angles. So if this is X, this is the angle X over, whoops, somehow into erase. This is angle X over here. So then this would be angle X over here, right? Because I have two parallel lines. And then if that's X, then the stuff above it has to be 90 minus X. And because I have a right triangle, then this has to be X over there. So EA is the opposite side to angle X with a triangle of hypotenuse sine of Y. So it's going to be the hypotenuse times the sine of X, which is the sine of Y, sine of X, because the hypotenuse is the sine of Y. And so putting it all together, we get OD is OC minus DC, which is cosine X, cosine Y minus sine X, sine Y. All right. You should have seen something like this and then put this, somewhere in your trauma files. This is the geometric proof of the angle addition formula, subject to the assumption that X, Y, and X plus Y are all less than 90 degrees, so that I can draw this in the first quadrant and not worry about things exceeding. So technically I have to work, well, what if X plus Y somehow goes beyond over here and deal with that? Okay. I am assuming no one wants to be responsible for this on an exam. Okay, the purpose of this is to show why you're taking a class like multivariable calculus, why you're learning all of this stuff. Okay, it's also much better to do this on the iPad with all these colors available than in the old days when I did it with just white chalk. So you can see things a little bit more clearly as to what's going on. This is not a hard proof. This is really a follow your nose. Just keep writing things down and mining relationships until you get what you want. Just keep drawing triangles. And all right, I don't have enough yet. Well, what do I know that's similar to this? And just keep playing games. All right, let's see how to do trig by calculus. So we know e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot 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 is the sum, n goes from 0 to infinity, of x to the n over n factorial. And then if we do the exercise, we see cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus dot dot dot. And sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus dot 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 dot. And again, you can see that by doing the Taylor series and just doing the derivatives patiently. We talked about the following. E to the x times e to the y is e to the x plus y. Okay. Technically, this needs to be proved. E to the x is an infinite sum. E to the y is an infinite sum. Their product is the product of two infinite sums. If this were not true, the notation would suck, right? You can prove this. We will prove it later when we do multivariable calculus and we talk about double integrals, which is really the same as double sums. All right, why does this matter? What is the most important, your go-to identity from trig? Your relationship. What is the first relationship you think of in trig? The first equality. When you think of your trig functions. What's the first equality involving more than one trig function? What's your go-to? Sine squared plus cosine squared x equals 1. So we have Pythagoras. So e to the ix times e to the minus ix is what? E to the 0, which is 1. But this is cosine x plus I sine x times cosine negative x plus I sine negative x. Okay. And so here we're using e to the ix is cosine x plus I sine x. And note, cosine of negative x is cosine x, sine of negative x is negative sine of x. This is because cosine is an even function. Cosine of x is cosine of negative x. Sine is an odd function. Sine of negative x is negative sine of x. You could also see that by using e to the minus ix. This is the complex conjugate. If you've seen this before, you basically replace all the i's with minus i's. Would be cosine x minus I sine x. And that's the same as cosine of negative x plus I sine negative x. All right, well, why is this useful? Well, if I take what I have over here and I multiply things out, cosine x times cosine negative x is cosine squared x. Then I have an I sine x cosine negative x. Let me do it more slowly. So I will have cosine x plus I sine x times cosine x minus I sine x. So cosine times cosine is cosine squared of x. I sine x cosine of x minus I sine x cosine of x. They cancel. The middle terms cancel. And then I have I sine x times minus I sine x. What's I times minus I? It's I times minus I is minus I squared. I is the square root of -1. So I squared is -1. So minus is a positive. So this is minus I squared sine of x. This is just cosine squared x plus sine squared x. So there is the Pythagorean theorem. And again, we're getting this immediately from our series expansions. All right. All right, did everybody memorize this? Yes. You're going to want those knowns back later. All right. So you've got that horrible geometric proof. So let's look at the angle addition formulas. E to the ix times e to the iy is e to the what? So e to the ix times e to the iy is what? E to the ix plus y. And then this would be cosine of x plus y plus I sine of x plus y. And now we can expand. This is cosine x plus I sine x. This is cosine y plus I sine y. Now, let's expand and let's put all the real stuff together and all the imaginary stuff together. So cosine x times cosine y, that's real. I sine x cosine y, that's imaginary. So I'm going to put that over here. Then the next term I'm going to get is cosine x plus I sine y. That's also imaginary, so that's going to go here, cosine x sine y. And then the last one is I sine x times I sine y. What's I sine x times I sine y? Negative sine x sine y. So if a plus ib equals c plus id, then a equals c, b equals d, if a, b, c, and d are real numbers. So the only way two complex numbers can be equal is if the real parts are the same and the imaginary parts are the same. So cosine x, cosine y has to be, I'm sorry, cosine x plus y has to be cosine x, cosine y minus sine x, sine y. Yes. So I is the square root of -1. So I squared equals -1. You might have seen this when you were solving quadratic equations, ax squared plus bx plus c, and you have the solutions on -b plus or minus square root of b squared minus 4ac over 2a. So they called b squared minus 4ac the discriminant. And if that was negative, then you have two roots that are complex conjugates of each other, because you'll have the square root of a negative number. So the only place you've seen probably I before is when looking at roots of quadratics. When I was in grad school, one of my friends was a high school math teacher, and they misprogrammed the calculators. This was a long time ago, and calculators were not as good, so that it gave the right answer if your polynomial had only real roots, and if it had pure imaginary roots. But if it had complex conjugate roots, it gave the wrong answer. And they didn't know how to reprogram the calculator, so they just had to be very careful not to get it. It was terrible. So we just did the real part. Well, the imaginary parts have to be the same. So there's your formula for the sine of x plus y. You can get it immediately from this. Compare this to the inspiration we needed, drawing all the lines, looking at all the differences and whatnot. You do get some return for learning calculus. All of these trig relations, if you want to get the sine of 3x, if you want to get formulas like that, if you want to get the sine of x halves, we can do all these formulas really nicely just by knowing a few key things from trig. So the big items, e to the ix is cosine x plus I sine of x, and e to the ix, e to the iy is e to the I x plus y with I squared equals -1. Okay. So this gives us, some more ways of calculating Taylor series. It gives us some applications to trigonometry. And I've hopefully convinced you by reminding you of the long way that your teacher hopefully did things that, there is an advantage to learning these Taylor series expansions. Okay, did anybody have any questions from stuff from chapter 10 that they wanted me to discuss? Okay, so for the last little bit of time today, imagine I give you, say, f of x, y is sine of y cosine of x plus y. Okay. Any thoughts on how I might try to expand that? So to be perfectly clear, we haven't done multivariable differentiation. We haven't done multivariable Taylor series, and I'm still asking you the question. Are there any pieces that you understand how to expand? Sine of y. So we know sine of y is y minus y cubed over 3 factorial plus ... What does the cosine of x plus y look like?
To distribute.
So one thing is we could distribute the cosine, and we could write this as a bunch of functions. So one possibility is to distribute cosine of x plus y would be cosine x, cosine y minus sine x, sine y. That's one thing we could do. There's something else we could do. So we had 3 different techniques. One of the techniques was to put in some variable u, do the series expansion for u, and then replace u with what you want. What should I take u to be here? X plus y. So cosine of x, of u is 1 minus u squared over 2 factorial plus u to the 4th over 4 factorial minus ... Take u equals x plus y. And so you get cosine of x plus y is 1 minus x plus y squared over 2 factorial plus x plus y to the 4th over 4 factorial plus ... minus ... So this is 1 minus x squared plus 2xy plus y squared over 2 factorial plus x to the 4th plus 4x cubed y plus ... plus y to the 4th over 4 factorial plus ... and this is a minus ... And then we could multiply them together. And so if I have a complicated function, I can often reduce it to understanding simpler ones. And so if I start to multiply things out, I would get sine of y times cosine of x plus y. Well, let's see. There's going to be no constant term because whenever I hit here, I'm going to get at least a y. So I could have 1 hits y, and that's going to be a y. Is there going to be any x term? There's no x terms. There's 1 y. Could I get any x squareds? Nope, because I'll have to have at least a y hitting it. Can I get any xy? Nope. Can I get any y squared? Nope. I'm going to have no terms of degree 2. So I'll put these in different colors to highlight. So no x squared, no xy, no y squared. What about x? What about terms of degree 3, where I have 3 x's, 2 x's, and a y? Yes, I could have an x squared y. So I'm going to get a minus 1/2 x squared y. Then I'm going to have a minus I'll do it over 2 factorial. A minus 2 over 2 factorial xy squared, and then minus 1 over 2 factorial y cubed. Okay, so I can start to get something out. And then when I'm looking at this, I might want to try to figure out, how did these terms relate to derivatives? With Taylor series, okay, well, let's go back. This is the nice thing about having everything like this, is I can just keep rewinding, and eventually, okay, I just keep taking more and more derivatives. So when I start to look at what I'm getting over here, I want to be having things in terms of more and more derivatives. So I want derivatives of this with respect to different variables. Well, we haven't really defined yet what differentials mean when we have functions of several variables. So what we're going to do right now is we're going to just jump ahead and very quickly define partial derivatives. So it takes less than a minute to learn partial derivatives. When I was younger, I used to have people time me, but it's not even close to a minute. So df dx means take the derivative with respect to x, holding all other variables constant. That's it. That's essentially half the class. So if I give you, say, f of x is 3x squared plus 17x, what's f prime of x, which we're going to write in a better notation, df dx? What would that be? Let's add an 8. What would df dx be? 6x plus 17. Now let's say I give you f of xy is x squared y plus 17x plus 8y cubed. And now I'm going to use the strange d. This stands for partial derivative with respect to x. So I take the derivative term by term, and I consider anything that's not an x to be constant. So I'm not allowing y to change. I'm keeping y constant. What's the derivative of x squared y if you view y as a constant?
2x.
It's just 2x. Just 2x? 2xy. So really, I should view this 6 as 3 times 2. What's the derivative of 17x? What's the derivative of 8y cubed? With respect to x, what's the derivative of 8y cubed with respect to x? 0. And there you go. So you've just learned how to do partial derivatives. What would be the partial derivative of f with respect to y? So now I hold x constant. What's the derivative of x squared y where x is constant? X squared. What's the derivative of 17x? And what's the derivative of 8y cubed? 24y squared. So we've now figured out how to do partial derivatives. And it kind of makes sense. What we're doing is keep all the other variables constant. So I really reduced it to a one-dimensional problem. It's just, what's the notation? So the notation df dx generalizes better to partial f, partial f. So read as partial f, partial x. And then for something for you to think about is you can go back over here and try to figure out, how do these relate to derivatives? And then you have to figure out, what do we think the second derivative should be? And then we have different orders. I can take the derivative with respect to x. I can take the derivative with respect to y. Does it matter if I take the derivative with respect to x and then y? Is that different than taking the derivative with respect to y and then x? If I want to have terms of degree 2, I have lots of different ways. I could do 2 derivatives with respect to x. I could do 1 with respect to x, 1 with respect to y. I could do 2 with respect to y. So we'll get to all of this later. But if you want a challenge, try to figure out how these are related to the possible first, second, and third derivatives you could be doing. All right, so this is a good place to start. All right.